Welcome to the Hydrology course. I'm really excited about teaching this course after doing several one-day seminars on hydrology for soil and water conservation districts. I'm looking forward to kind of expanding on those hydrology topics and hopefully getting other people interested in it. Just a note, if you're here and you work primarily in urban hydrology, we will be covering the basics of urban hydrology and also agricultural rural hydrology. So you'll see references to agricultural BMPs and urban BMPs and the hydrology to come up with design flows for each. Now, what are some of the BMPs that need hydrology studies? We've got diversions, wascobs, terraces. These are all agricultural practices. Closed drainage networks are typically in urban areas. Flood control can be both. Green infrastructure practices are typically urban again. Stream restoration is typically rural, culverts, manure storages. And the thing I want to highlight is that some of these practices only require peak flow rates, and others require you to know the entire storm volume. So a peak flow rate is achievable, say, using EFH2 or the rational method, but in order to get the whole storm volume, you'll need something more complicated. So that's just something to keep in mind. If you need the whole storm volume, you'll have to develop a hydrograph and use a method that provides that. And we'll cover what a hydrograph is in a moment. So first off, I want to give you a sense of what is the best method of hydrology. You know, how we're coming up with stream flows or storm volumes. What's the best method? The best method is stream gauge data. Okay, this is an actual historical record of storm flows at a site. Okay, obviously the problem is stream gauge data only exists for streams of a certain size, and most of our hydrology studies are for small watersheds. So it's rare to find a stream gauge near your site unless you're doing a bridge opening or something. Okay, the next best option is regional curves developed from stream gauge data. And these are really useful, except that they have the same kind of size limitations as stream gauges. Okay, the regional curves are developed from stream gauges, so they're only effective on watersheds down to the smallest stream gauged site in your region of the state. Okay, so you can't use them on your 1 acre watershed leading to your catch basin. Okay, next best is how we get into hydrologic modeling. Okay, so the SCS, formerly called SCS, now it's called NRCS. They have two methods. For rural sites, you can use EFH2. For urban sites, you can use TR20, which is sometimes called TR55, which is the pen and paper version of the TR20 method. And then finally, I'd say the least reliable is the rational method, although it's still quite commonly used for catch basin closed drainage network design. And for that, it is fine. So let's talk a little bit about where you learn more about each of these topics, because we're not going to cover them all in this course. Okay, for stream gauge data and regression curves, you need to go to your state stream stats program. For New York, it looks like this, and each stream stats program has background documentation. For New York, it's these two documents. Lumia and Freehofer is magnitude of frequency of floods in New York. That covers drainage area and peak flow, I believe. And then this one covers bankful, discharge, and channel characteristics. So for New York, we have two components of stream stats, one for the bankful channel cross-section and one for the magnitude of frequency floods. All right, how about TR55 and EFH2? Those are both derived from the National Engineering Handbook, Part 630. Okay, it used to be called NEH Section 4. It's an NRCS publication. It's hundreds and hundreds of pages. You do not want to read it, but there's two derived documents that are worth reading. EFH2 for agricultural lands. It's only 7 pages. Download it from the NRCS website, or I've attached it here as an attachment to this lecture. TR55 is also a good resource. Like I said, it's kind of the pen and paper version of the TR20 method. And the TR20 manual isn't really helpful because it's a software program. But the TR55 manual is really helpful. It goes through the steps and how each equation is derived and how to use it. And I've also attached this to this lecture. Okay, in the rational method, since we're New York State, I'm going to recommend the New York State DOT Highway Drainage Manual, or Highway Design Manual, Chapter 8, Highway Drainage. Okay, it has a nice little section on the rational method and kind of where it came from and how to use it. But we will be covering the rational method in this series. So I mentioned hydrographs before, and you might be asking, what is a hydrograph? Well, it just shows the flow rate in a stream over time. Okay, in our cases, we're going to be developing hydrographs for a set amount of time, typically a design storm length. But this is just a regular one for a river. It's East Branch Delaware River after Hurricane Irene. You can see, before the flows reached the gauge, it was, this level, just over 1,000 CFS. And then once all the water in the watershed got down to this gauge, it reached a peak. And then, after the storm was over, it kind of gradually settled down. They had some flood control measures, which is why this is level. And then they let more water out and, gradually went down. So this is kind of what we're looking at when we think of a hydrograph. This top is just the peak discharge. And a lot of our practices, we only need the peak discharge. This time window from when the flow at the design point, or the gauge, when it starts increasing to the peak discharge, that's called the time of concentration. That's the time that it takes the furthest raindrops in the watershed to flow all the way down to the design point. Now, different watersheds are going to have hydrographs with different shapes, and I'm going to cover that in this slide. On this side, it shows the effective basin size on the hydrograph. So a very small watershed. Well, I wouldn't say this is small, 1 kilometer squared, but it's a small peak flow with a short time of concentration. As the basin size gets bigger, obviously the peak is going to get bigger, but also the time of concentration will increase as well, right? So in this first one, it only takes a short time for the furthest drops to get to the design point. In this one, it takes much longer for the furthest drops to get to the design point. Okay, and basin slope and shape is going to make a difference too. Okay, if you have a basin that's steeply sloped and elongated, you'll have a short time of concentration with a high peak. The more diffuse it is and flatter, you'll get a lower peak discharge and a longer time of concentration. I think in this, for these 3 examples, they're all the same area, say in square kilometers, but they're each going to have a different time of concentration and peak flow. Now, one thing to consider is storage in the watershed. If there's ponds or wetlands in your watershed, you need to take those into account because water in your watershed will collect in those areas instead of just flowing straight down to your design point. And you can use NEH 630 to estimate the peak discharge in watersheds, in rural watersheds, I would say. In urban watersheds with storage, you should break it up into sub-watersheds and use a modeling program such as HydroCAD to figure that out. But I think for rural sites, you can use NEH 630. They have adjustment factors for ponds and wetlands to help you figure out what the modified discharge would be for those. Now I want to talk about rainfall distributions. We're trying to come up with how much runoff runs off a site, so we need to know kind of how much rainfall hits the site. And we want to know how intense is the heaviest rainfall, because that'll produce the greatest the flow rates for our BMPs. Historically, we had synthetic rainfall distributions called Type 2, Type 3, etc. It was a storm duration of 24 hours, and the intensity of the rainfall varies over the storm period. In 2013, the Northeast Regional Climate Center updated rainfall distributions for the Northeast United States, and New York falls in that. So we should be using the new rainfall distributions type A, B, C, and D. And these are also 24-hour storms. You might be asking, what is a synthetic rainfall distribution? Why do we use it? Well, I'm not going to explain that right now, but I want you to go to TR 55 at Appendix B and read the sheet on synthetic rainfall distributions. It's actually a pretty handy tool for doing hydrology, so that everybody can be using a uniform formatted data. We can get individual rainfall amounts, but we're coming up with intensities that are kind of uniform across the field. So if you're looking for the synthetic distribution type in New York, you can go to this map on the NRCS engineering website for New York. And it just has all the counties, and it says whether you're A, B, C, or D. Okay, if you're on one of these tiles that is a border between two of the types, there's blow-up maps of those, and it'll show which towns are in which types. And then finally, I want to just show you the distributions. This is what it looks like. This is a synthetic rainfall distribution curve. On the left, you have the cumulative rainfall fraction. So at the top, at the end of the storm, you've received 100% of the rainfall. That would be 1 times however many inches of rainfall that storm produces. 12 hours is right in the middle. And then for each specific storm length, say if you have a 1-hour storm, you're going to be sampling the rainfall 30 minutes on either side of this midpoint. Okay, so that's how, if you read the Tier 55 Appendix B, it says the storms are nested. So kind of the 5-minute storm is nested inside the 10-minute, is nested inside the 30-minute. Okay, so for each design storm, we're looking at kind of half the length on either side, making up a total time duration. That's all I want to cover in this introduction. I'm attaching those reference documents. Definitely browse through those so you get a sense of where to learn more and where to look up answers to your questions. Probably the most important step in doing hydrology is creating an accurate drainage area. And to create an accurate drainage area, you're going to need accurate contour lines. Now there's basically 3 ways we can get contours. We can do a survey ourselves, we can rely on flown Lidar scans, or we can rely on USGS topo maps from the 60s and 70s. And I'm going to just talk a little bit about both and how we can combine them. First up, you might have a survey that you've done with a total station, or you could have a grid survey done by using your level. And if you input that into, say, EFT or Civil 3D, you can develop triangles, and from the triangles you can develop contours. This is probably the best bet, but oftentimes we don't survey the entire watershed of a practice that we're designing. We'll just design the site area needed to construct it, and then kind of fill in the watershed contours with something else. For example, a Lidar. So Lidar is available for, I'd say, 1/2 to 2/3 of New York State. You can get it from the GIS clearinghouse, download it, process it in ArcMap, display contours, what have you, and then delineate the rest of your watershed using these contours. Then finally, in areas that we don't have Lidar coverage, you can use USGS contour maps. And these are also available as digital elevation models from the clearinghouse, so you can play with them in GIS as well. They're not quite as accurate as the Lidar, but they're generally suitable for kind of large size, low detail watershed studies. With any drainage area mapping, you're going to need to ground truth it after you've mapped it out. So here's kind of the basic principles of drainage area delineation using contour maps. The first thing to do is come up with a design point. Okay, a design point for most structures will just be the structure itself. Say for a manure storage, or for a catch basin, or for a pond, the design point is just the structure itself. For a linear structure such as a diversion, your design point will be the most downstream point. Okay, so you want to start from your design point and then go up into the watershed, going perpendicular to the contours. And when you're doing your delineation, you'll be looking for hills surrounding the watershed, and you'll be connecting lines between the hills. So in this watershed, these 2 hills represent border points on the watershed, and the other border point is this saddle between the hills. You can look at the contour shapes to help you do your delineations. On water courses, they always point uphill. See these contours kind of bend and make an arrow? They point uphill. On a nose of a hill, see there's no water course in this area, the contours point downhill. So in this watershed, you'd be coming up perpendicular to the contours, up to the top, across, and then back down. So ground truthing is really important, especially if you have roads or man-made features, because they don't always get picked up in the Lidar. You might see it as kind of a jagged contour or a little blip, but it's not very apparent. So it's really important to be able to walk your watershed to get an accurate idea of the map. Now GIS has some tools for hydrology, and they are useful to some extent. However, they're mostly geared towards doing hydrology for existing streams. If you're creating a new structure, say a new diversion, you won't be able to delineate the drainage area for that using, say, a DEM or a Lidar geotiff. You'll need something with existing streams in it. But if you are working on a stream, computer models can be great. So this is StreamStats, as most of you should be aware of, for New York. Its kind of limitation is that you can only delineate areas that are located on one of these blue line streams. So you have to be zoomed in far enough for these to appear, and then you can only do watersheds small enough on these. But all in all, the computer methods are kind of neat because they'll give you ideas for how the water might flow that you might not otherwise think of. Here's kind of a similar delineation in ArcMap for these two points. They're on existing water courses, and these are the delineations that ArcMap came up with. Like the shape of this and the shape of this, it'd be pretty hard to come up with that on your own just using hand methods. So let's jump over to ArcMap, and I'm going to show you a couple demos of delineating watersheds kind of on the fly. This is a good time to talk about GIS in this course. To get the most out of this course, you should have some way to manipulate LiDAR data, DEMs, and TIFFs. And to do that, you'll need ArcMap's Spatial Analyst add-in, which requires an ArcMap Advanced license. I know many of the soil and water districts might not have an advanced license or Spatial Analyst add-in. And if that's the case for you, you should look into downloading QGIS or QGIS and using that for the Spatial Analyst features it has. It's a free program, and it has most of the Spatial Analyst tools that we'll need built in for free. If you do have ArcMap with the Spatial Analyst extension, you'll be all set. And later on in the course, I'm going to be showing workflows for hydrology stuff using both packages, both with QGIS and ArcMap. For this course, I'm going to assume that most people have kind of a basic understanding of ArcMap or GIS and how to use it, but I'm going to go pretty slow to make sure that everybody's on the same page. And if you're using QGIS, it's going to be a little tricky because you have to add the topo maps first, but I'll show you how to do that quick. Just go to a browser and search for USGS Web Map Service. That should give you to this page, the National Map Service Endpoints. Okay, and you want the National Map Viewer tab on this, not these other two. And then I've had good luck with all the tiled map services. The dynamic ones, I can't get them to load for some reason. So just go with this first one, USGS Topo Base Map Primary Tile Cache. And you want to click on the link over here where it says WMS. Click that. It'll display an address up here. You want to copy that. So I'm just going to do Control-C to copy it to the clipboard. Close the browser. Go back to QGIS, and here you want to select the button for WMS service. It's this globe with a plus sign over on your primary toolbar. Click that. Do a new service. You can call it USGS Topo. Then you're going to paste the URL in there that you copied from Google. Okay, and do all right on that. So now that connection is set up, you need to connect to the server. Click Connect. It'll show you all the available layers for that service. Click on the one you want. Give it kind of a logical name. In here, you can just, name it whatever you like, and click Add. And that'll add that web service to the map. Important to note is that these services are scale dependent. If you zoom in too far or zoom out too far, they'll just disappear, and you'll be like, where did that go? So this one, if you zoom in, I think it's past 1 to 10,000, it's gone. But you can zoom out pretty far and see how much your state or country you want. So to do some watershed practice, just find an area, say in the Adirondacks, where there's a lot of topography, and create a new shapefile. You do that by going to Layer, Create Layer, New Shapefile Layer. It's going to be a polygon, just like we saw before. Select the coordinate system. Let's use NAD 83, Zone 18N. We don't really want to add any more attributes. If you want to add attributes for land use or whatnot, this is where you would do that. I'll click OK. It's going to ask us to save it somewhere. I'm going to save it over this watershed practice shapefile. Replace it. Yep. Okay, so now I have a shapefile ready to edit and put my practice watershed into. Now you're going to look for the editing toolbar. It's this one up here. There's a little pencil to turn editing on. You click that, and then to draw your watershed, you use the Add Feature button, which looks like a little kidney bean with a star on it. Add Feature. Look for your design point, and then trace up through the watershed. And right-click to close. Here's where you enter your ID. It doesn't have automatic numbering, so you have to remember what else is in the shapefile. So we'll do this as number 1. Okay. And if you need to edit vertices, that's this tool up here. It looks like a little joint. Okay. You click near one of the nodes, and then you can move them around. All right, and then save edits and turn off editing. All right, have fun. Hopefully by now you're somewhat comfortable with delineating watersheds using USGS contour maps, but let's look at how you can use Lidar data in New York to get a little more detailed view of the contours. So you should know about the New York State GIS Clearinghouse already if you're working in a soil and water district in New York. So just browse to that. If not, just Google search it. Once you're on the home page, you click on the ortho imagery link here, and then start the ortho imagery application. And this is their kind of a web map portal where you go to download aerial photos if you want to use those in GIS. First, click over on the layers button over on the right, and let's turn off all those orthos. That'll let us see what DEMs are available better. So the lidars are stored as DEMs. That's a digital elevation model. And you see all these different options, all the way from 0.7 meter resolution. That's the distance between points in the grid. So a smaller meter number means that it's more accurate. 0.7 meter all the way up to 10 meter. Now these 10 meter DEMs are just derivations of USGS contour maps. They've been scanned in and digitized. So they're no better resolution than the contour maps, even though they are digital. So let's turn that off and turn on all the other ones. And all these other ones are derived from LiDAR scans. So if you're trying to get an idea of what's our overall coverage in New York for LiDAR, this is basically it. It's all of Long Island and some of the southern tier, and then kind of scattered counties in between and around. So hopefully you're in a county that has LiDAR coverage. If not, then you don't get to use it. All right, so let's look at how to download it now. Say we're over here in Livingston. As you zoom in, it'll limit your layers to only the ones available in that view. So that's kind of nice. I'm going to turn them off for now and find a farm that we can use as an example. Let me make sure to get one that's on a border. How about right here? All right, so say our project is in this area. Okay, 1 meter DEM index, USDA, UTM 18N. That is the layer that's available, and it shows that there is coverage in that area. So to download it, you go to this download folder over here. It's a folder with a little arrow on it. Click on it. I usually do current view. And then it'll give you the option to download orthos. But we don't need those. We're going to use a web service for those. So we want DEM results. Show tile list. And then each of these image files needs to be downloaded separately. Just right click it, do save link as. Then I'm just going to put it on my C drive in the Cortland folder right here. Save that one, then do the right click, save link as, same folder, save it. Alright, now let's jump over to GIS and see how we load those and generate contours. If you're using QGIS, the process is a little bit different, so let's walk through that. Once you're got QGIS open, you look for the Add Raster tool over here on the left. Looks like a little checkerboard. Okay, and browse to the files that you want to add. Livings 310 and 311. Let's just do one at a time on this one. I'm going to do Livingston 310. Open it, and that displays in your viewport again. It looks a little bit different because the shading is set to a different setting on this one. Now, the important thing to remember in this one is that the QGIS contour tool doesn't have a Z-factor conversion built in, so we need to convert the raster to English before we even go and try and do contours. So to do that, you're going to go up to the raster menu, raster calculator. Okay, and this is where you can manipulate the values that are in the raster. So over here in the main window, you have values of 363 to 369 meters, and you want to convert that to feet. So what you're going to do is take your raster bands, this Livingston 310 band 1, you can double click that, and you just want to multiply that, here's the star key, by that same conversion factor that we used before, 3.2808. You need to set it a file to save it to. So I'm just going to save it in the same folder and call it Livings 310 feet. Click OK, and that'll calculate it for you. Alright, and it's added it to the map too. So you can see instead of 363 to 369, it's now 1112 to 1209. So let's unclick that one and remove it from the map. And now let's generate contours for this one. And this is going to be up in the raster menu again. Come down to extraction and contour. And here we need to select the raster, okay, Livings 310 feet. And it's not going to put it in a file Geo database like ArcMap, it's going to put it in a shapefile. So we need to give a name for that. We'll just do Livings 310 feet dot shape. Okay, the interval is going to be 10 feet again. And we don't need attribute data. We're going to leave that unchecked. Click OK. Processing complete. OK, OK, close. And there's your 10-foot contours on the raster. So go ahead and use those. Again, if you zoom in, they're super bumpy, so don't use the computerized distance for your line lengths in the average slope method. Remember, The average slope method contour length technique is designed to use hand-drawn USGS contours, not machine-drawn wiggly Lidar ones. All right, so if you don't have spatial analysts, go ahead and fire up your QGIS and try and get one of these DEMs to load and contour it. Once we have our drainage area mapped out, we need to determine what fraction of rainfall comes off the ground in runoff. We know a portion of it will soak into the ground, and that won't be available to our drainage best management practice down at the bottom of the watershed. And in the NRCS methods, the runoff fraction is determined by two factors: a land cover type and a hydrologic soil group. So check out this table here from TR55. You can download the full TR55 manual as an attachment to the introductory lecture. If you look through it with me, the first section is for fully developed urban areas, and there's different types: impervious areas, parking lots, streets, open space, lawns. And then for each hydrologic soil group, there's a different rating. We're going to cover hydrologic soil group in just a moment, but as you can see, the A soils have a lower CN value, and the D soils have a higher CN value. And the higher the CN value, that means the higher the rainfall fraction will come off and run off. If you scroll down, you can see there's another table for cultivated agricultural lands or croplands. And in these, it's important to note that there's ratings for different hydrologic conditions, poor or good. And the difference between poor and good is basically a design decision that you'll have to make. Two people looking at the same field might give it different ratings. That's okay, it's your designer's preference. Keep going down, there's another section for other agricultural lands, like pastures, meadows, brush, woods. And if you keep on going, there's one for rangeland too, but we don't really have much of that in New York, so you don't have to worry about that. Now getting back to hydrologic soil groups. The hydrologic soil group rating is not really for the top layer of soil, it's really for the whole soil profile. So this is the table that shows how they rate hydrologic soil groups for each soil type. It's from part 630 of the National Engineering Handbook, and it just shows they're considering the depth to the impermeable layer. So that might be the water table or bedrock or some other impermeable layer. Okay, depth to high water table by itself. The saturated conductivity of the least transmissive layer in the depth range. What depth range and what depth range that occurs at. So they basically go through this tree and figure out what hydrologic soil group it should be. So the important thing to remember is it's for the whole soil profile, not just the top little bit. And lastly, on runoff coefficients, I want to talk about C values used for the rational method. Typically, we don't consider the hydrologic soil group when using the rational method, and we typically use the rational method in urban areas. So a lot of people count this as a strike against the rational method, or at least its implementation, that we don't use hydrologic soil group. But I found that it does work fine for urban storm drainage networks, and it's really quite simple and easy to use. Now let's talk about how you would look at your watershed, chop it up, and assign CN values to each part. Here's an example watershed. There's 5 different soil names, but only 2 soil groups. So this pink part is group C, and then there's a little strip of group B on the inside. That kind of covers the areas of hydrologic soil groups, but we also need to merge in what the land use is in each area. Suppose there's 3 sections of land uses of 2 different types: pasture, good condition, and woods, fair condition. If we overlay those, we'll get 5 sub-areas: pasture good, group C; woods, fair, group C, etc., etc. So the process of hydrology modeling is chopping up your watershed into all these little sub-areas and then combining like types and creating a weighted CN value. Areas with a higher CN value are going to get more weight if they have more area, and areas with a lower CN value will get less weight if they have less area. And fortunately, we have software that helps calculate these weighted averages. Here's EFH2. It just has a chart on the RCN tab where you type in your land use, number of acres of each soil group, and it gives you a weighted CN value. Here's a similar input for HydroCAD. You open up your watershed, then select curve number, and it has the same basic stuff, all the different land types, all the different soil groups, and descriptions of each. One other thing to consider, you can get your land uses just by looking at the land, but where do you get the hydrologic soil group? There's a couple sources for that. First up, there's county-specific tables for hydrologic soil group in ePhotog. All right, so say you're in Cortland County, you can just download all the soils for a chart with all the soils for Cortland County, and it'll have each hydrologic soil group. Alternatively, there's a chart for the entire state that lists all the soils in the state and their hydrologic soil groups. There's Web Soil Survey. Hopefully you're familiar with this. If not, just Google Web Soil Survey and poke around in it a bit. It's really quite neat. And in the Soil Properties tab, you can display the hydrologic soil group. And then finally, Soil Data Viewer is an extension for ArcMap. You don't need anything beyond the basic ArcMap license. It's an extension you download from USGS, and it makes this little viewer and enables you to display maps of basically any of the soil properties that you can find in Soil Data Viewer. It can display in ArcMap. All right, and we're going to cover basically how to create a map with all these soil groups in it, and how to chop them up into different land uses and hydrologic soil covers. And we'll be using GIS to do that in the next couple lectures.
Getting soil data for QGIS is different from the workflow used in ArcMap because we can't use the Soil Data Viewer Esri plugin. Instead, we'll download the data as separate shapefiles and tables and then join them together inside QGIS. So just Google search for Web Soil Survey. That's where most of the data is going to come from. Once you get to the Web Soil Survey page, you can click the green button to start Web Soil Survey. And then instead of zooming in for our area of interest, in this we're going to be finding soils data for a specific county in New York State. So you'll look for the tab, Download Soils Data, and then download the soils data for Soil Survey Area, SURGO. Then in the state dropdown, we'll pick New York State. County, we're going to do Cortland County. And once you have those two populated, it'll give you a data bar down here with a soils data download link. Okay, and once that's downloaded, you can go to that location and then cut that, extract it, paste it, whatever you want to do to extract to a folder of your choice on your PC. So for Cortland County, it should be called NY023. Now if you open up that folder, you'll see several folders and several files. The spatial folder contains shape files of different types. The tabular folder contains tabular data, which is mostly unreadable to humans. It's for importation into an Access database. The README file has instructions on how to use this whole thing. These two files are metadata, and then the Soil Database US 2003 is a Microsoft Access template database. It's used for preparing the data to be used in Soil Data Viewer, but we'll also use it later on in just a minute. For now, all we're going to be using for this, for New York, is the spatial data shapefile. Okay, the next thing we need to download off the web is the soil hydrologic groups. That's key information for our hydrology studies. And in New York State, you can get that data from the New York State ePhotog. The staff in New York have helpfully provided an Excel sheet. They update it every year with hydrologic soil groups for each of the soil types across New York State. This isn't available in every state, So if you're outside of New York State, just stay tuned. I'll cover a brief methodology for that in a bit. So for New York users, try and find the New York ePhotog. That's Field Office Technical Guide. Select your state. It's going to be New York. And then once it loads up, just do a document search for Hydrologic. Okay, and you'll see the first hit is this one, Hydrologic Soil Group Data for New York 2021. So click on that to download it and put it in an appropriate folder. I'm going to put it right in the New York 023 folder. And if you open up that up, you'll see what's in it. It's got a nice header here. It's got an area symbol, area name, all these fields. The field that we're particularly interested in is the hydrologic soil group. When we do our land use classification, we'll intersect that with this data to figure out how much runoff comes off each parcel. Now, in order for this data to be matched up with data in the shapefiles, we need a common data key in each file. And in this case, it's called the MU key, or map unit key. So these map unit numbers are all unique identifiers for each soil type. Each soil type has its own hydrologic soil group, so we'll use these keys to match the hydrologic soil group to the actual shapefiles in the next step. Now, unfortunately, QGIS cannot access an Excel file just like this, so we're going to have to save this as a comma separated values file. So to do that, go to File, Save a Copy, and then under the file type, you're going to pick CSV UTF-8. That's comma delimited. I'm going to rename it Hydrologic CSV and click Save. Okay, so now that that's done, let's go over to QGIS and we'll open up the shapefile and make sure it looks right. Now, just as a disclaimer, this part of the lecture is kind of an update, so I'm using a later version right now, version 3.22, than I'll be using later in the course. Okay, so to add the shapefile, we're going to go to Layer, Add Layer, Add Vector Layer, and then under the source, click to Browse, and mine is in Documents, QGIS, NYO23, Spatial, and then you just want the first spatial file. You can look over here, and actually on my computer it's listed as an AutoCAD shapefile, but on your computer it should just be listed as a shapefile. Okay, leave all those as default and click Add. Okay, now zoom to that layer. All right, and here you have all the shape files for all the soils in Cortland County. Now if I open up the attributes table for that, by right-clicking on the layer, open attribute table, you'll see there's really not much information in this. There's the area symbol, that's just the file name, the general area where it comes from. Spatial version, I don't know what that means. The map unit symbol, these are the map unit symbols for each soil type. But here's the important one, it's the MU key. So the map unit key is going to be the data that we cross-reference with our Excel data to add a final column here for hydrologic soil group. So we can close that for now. And now we're going to add a comma-separated values layer to our QGIS project. So again, go to Layer, Add layer. Add delimited text layer. Okay, so here we're going to search for our CSV file. Which I just called Hydrologic CSV. We can stick with that layer name as well. For file format, it's CSV, comma separated values. For the record and fields options, this is going to sort through the headers and get rid of any that you don't want. So if I had that set at 0, it would read the comma separated values, first row, as the header values. So it would be this long sentence, and then in the Excel worksheet, these would have been blank. So it just substitutes in field 2, field 3. What we want is this line 2, to be in the header values. This other data is kind of garbage. We don't actually need it for this project. We want line 2 to be the headers and line 3 and so on to be the data. So for record and field options, we're going to discard the first 2 lines. Okay, we look down at the sample and that looks right. We've got area symbol, area name, map unit. We got all the right values in the header row. Okay, for geometry and definition, we need to make sure this is clicked no geometry. It's an attribute only table. There's no geometry associated with the CSV file. And then click add. Okay, so now that that's in our project, you can look at it, open attributes table, you can review it. So the next thing we're going to do is join that hydrologic CSV data to the map unit layer. So to do that, you're going to right click on the map unit layer, go to properties, look for joins on the left side, then click the plus sign to add a new join. The join layer, that's the layer we're adding to this layer, is going to be that CSV value, Hydrologic CSV. The join field, this is the field that's common to both files. So it's going to be something related to that map unit key, but it might not be called MU key in both files. In this case, it's MU key, all lowercase, in the CSV file. Then in the target, that's our current file, it's MU key, all uppercase. So they're pretty easy to match in this case. One is all lowercase, one is all uppercase. So those are the fields that we're matching up. Now down here in joined fields, by default, it's going to add every field from the CSV to our geospatial layer. But really all we want is a hydrologic soil group. So I'm going to select that and click hydrologic soil group. That way it'll only add that value to the table. Click OK and OK. Now when we go to the soil mu NY023 layer, go to open attribute table. We now have that final field in the table, hydrologic CSVs, hydrologic soil group, with a soil group for each map unit in the county. Now for states other than New York State, I checked a few and they did not have hydrologic soil groups listed on their ephotog in a nice spreadsheet like we do. So I'm just going to quickly cover where to get that data from Surgo if you're in another state. So basically, the files that you download from Surgo, in this case it's NY23, it comes with a soil template database, which is a Microsoft Access database that pulls data from this tabular folder and populates itself with a macro. So if you open that up, you'll probably get a macro warning. So you want to enable that content. And this is the wizard box that'll pop up. So you need to select the tabular data folder that has the tabular data that you want to populate into this database. In this case, it's right here. So I'm going to cut or copy, then paste. that tabular folder. Then click OK. And it'll chug away for a few minutes or a few seconds, depending how fast your computer is. Okay, once that's done, you can close out this one. Go over to your navigation pane, do the drop down and look for tables. And then the table where the data is located is called MUAGGATT. I do not know what it stands for. So scroll down till you get there, MUAGGATT. You can double click it to view the data. And if you scroll across, you'll see a bunch of different physical properties. And then finally over here, hydrologic group, A, B, C, D. Okay, and just to be sure, you want to check to make sure that this table has the map unit key, or else we won't be able to join it to the shapefiles. If you scroll all the way over to the right, you'll find over here, the last column is map unit key. So that's the column we'll use to join this data to the shapefile data in QGIS. So first we need to export this as an Excel file. So right click on the table, export, Excel, save it wherever you want it, then save as a comma separated values file, and then import and join that in QGIS the same way that I showed for the other Excel file that we got from New York State ePhotog.
Let's look at creating a weighted CN value map in QGIS. Now remember, the weighted CN value is going to be a combination of a land use type and a hydrologic soil group. So we need to be able to get those both into our map and intersect them to get the sums of those areas. Now what I have here is aerial photos of New York. This is just from the Clearinghouse. It's a web map service. If you want to get that, you can get it from this address or go to the Clearinghouse and cut and paste that address from there. And I also have the watershed that I created earlier. If I zoom in on that, here's what it looks like. Okay, so now that I have hydrologic soil groups, I need to create a layer that has land use in it. I'm going to actually turn that off and create a new layer up in Layer, Create Layer, New Shapefile Layer. Remember, it's going to be polygons. And the coordinate system I want to use is UTM NAD 83 Zone 18N. And this is a nice dialog because it lets you add attributes to your attribute table right when you correct the layer. And I do want to add one this time. I'm going to put in land use. It's going to be text, width is 80, that's fine. And then click this button to add to the attribute list. Okay, so now my shapefile is going to have IDs and land use attributes. Okay, select where to save it. I'm going to save it right here over this other one. Okay, now that we have our layer set up, we're just going to digitize this area, chopping it up into two types for this example. We're going to use pasture in good condition and woods in good condition. For your real projects, you probably have more than two types, and you probably have more detailed areas than I'm going to do, but this is just an example to get your head around it. The first thing in QGIS to remember is that the snapping is not quite as set up out of the box as an ArcMap. So in order to fix that, you'll go to Settings, Options. Under Digitizing on the left here, you need to go to Snapping and check this box, Open Snapping Options in a dock window, QGIS Restart Required. So if that's not checked, you need to check that and then restart QGIS to get the snapping options to working right. Click OK on that. And then if your snapping options aren't visible, you can go to Settings, Snapping Options, or View Panels, Snapping and Digitizing Options. And the most important part here is the snapping mode. It's default set to current layer. So if I want to digitize and snap to a separate layer, it's not going to snap to it. So I want to do snapping mode, all layers. Tolerance 15 pixels, that's fine. I'm going to move that off screen. So now when I go to land use, start editing with this little pencil, add vertices. That'll snap to that feature. It'll snap to
any layers in the project. In the original version
of
this course, this section used a file from an Esri geodatabase that I created outside of QGIS in order to bring hydrologic soils data into the project. For this update, simply use the shapefile that we joined hydrologic soils data to in the last chapter.
And then right click to end the shape. Now it gives you a little dialog to fill in your data. ID will just be 1. And land use for this, I'm going to be pasture, good condition. Okay. Now just go ahead and add in these other shapes. And I'm just going to speed up the video while I do that. Alright, now that we have that digitized, let's close our edit session and save it. And just check the attribute table to make sure that our feature names are all looking good. Alright, we have two types, pasture good and woods good, and they both match. You want the same spellings and everything with each type in this table. Okay, now that we have the land use and hydrologic soil groups, we need to intersect them to create little tiny areas of each type. So to do that, you're going to go to Vector at the top, Geoprocessing Tools, and Intersect. And just select your 2 layers to intersect in these drop downs. We're going to do Hydrologic Groups UTM, intersect with land use. And the output shapefile, I have an old one here, just going to call it intersect.shape. And click OK. Close. Alright, now I have an intersected shapefile of those 2 layers. If you open the attribute table, you'll see each area has a hydrologic soil group and a land use. Okay, so now we need to compute the areas of each of those each of those things. You see there's a shape area column here, but that's the map units, and we don't want that. We want it to be in acres for inputting into EFH2 or HydroCAD. So to do that, go to Field Calculator. It'll automatically start up an edit session on this layer, so you don't need to worry too much about that. We're going to create a new field and call it acres. It's going to be a whole number, 10 field, no, it's not going to be a whole number. We want a decimal, 10 wide and precision of 2. That'll be good. Okay, and then look at this list, and you're going to look for geometry. Expand that area. Double-click that area to add it to the expressions window. And then you need to multiply this times the conversion factor to get to acres. So the map units is meters in UTM zone 18. So we need a conversion factor to convert to meters. Fortunately, I have this saved in recent used functions, so I'm just going to go down to that. Recent area times this number, so it's 0.000244711 to get back to acres, and click OK. Alright, so now I have my acres column with each acreage of each little shape. I can close this, finish the edit session, save it, close. And now we want to add up those acres of each soil type and land use. And the best way to do that is with a pivot table. Fortunately, QGIS does have a pivot table plugin. It doesn't come standard with the installation just natively, but you can add it pretty easily. To add that, you just go to Plugins, Manage and Install Plugins. It'll connect to the official repository, and then scroll down and you're looking for Group Stats. So scroll down to G, Group Stats. And if this isn't checked, you'll need to do Install Plugin. Right, and just check the category on that. It's a vector tool, so that's where you'll find it in your menu options. All right, so if it's already installed, great. If not, install it. Close that. Go back to Vector, Group Stats. All right, and I have an old one here. You can just disregard that. We're going to be doing intersect. That's the layer that we want to do. And then these work just kind of like a pivot table windows in a Excel spreadsheet with a little bit of a difference. The fields we're going to be using are land use. Let's put these in the rows. Just drag and drop them. Hydrologic group and land use. Columns, I'm going to leave blank. And for the values, here's where you put what you're summing up, and you need to put a function in it. So we're going to sum up the acres, but it actually doesn't know that we want to sum it. We actually have all these options: average, count, max, median, min, standard deviation, sum, unique, and variance. So we want to tell it that we do want to sum them. So we're going to do sum of acres, categorized by these two fields. Once that's all set, click calculate, and it gives you your little pivot table right here. So these are the values that you'll be putting into EFH2 or HydroCAD to compute the weighted CN value of your watershed. And of course, if you want to split this up, you can drag these to different spots to make it a little bit easier to read. One thing I do want to stress on QGIS is that it's very sensitive to coordinate systems that aren't the same and having open edit sessions. So say you're editing your land use file, then you go to intersect something and it doesn't work. Maybe you forgot to save those edits, or maybe it's in the wrong coordinate system. So if you're going along and you have any problems with QGIS, definitely check to make sure that you don't have any edit sessions open, and that can be checked just by this little box here. It'll show a little pencil in it if you're editing that current layer, and you can have multiple edit sessions open on at the same time. So you might have multiple layers that are in edit mode, and you need to save edits on all of those before you do any geoprocessing tools. The next component of our watershed model to compute is called the time of concentration. Now this is the time it takes for the furthest droplets of water in the watershed to flow down through the watershed to your design point. And in this course we're going to be covering two methods, one for rural watersheds and one for urban watersheds. So let's look at how we do the rural ones first. We use a formula shown here. The time of concentration is based on three variables and some constants. We've got the watershed flow length in feet, the curve number, which we've already calculated, and the average watershed slope. So the flow length is pretty easy to figure out. You just draw a line through the watershed where you think the longest flow path is and measure it. The average watershed slope is kind of tricky to do, but fortunately we have some tools in GIS available at our disposal which help a lot. In the In the old days, we used traditional methods for computing the average watershed slope, and I do want to mention those here for your further interest if you want to research how to do these. They're definitely still viable tools and perfectly reasonable for your projects. We can do field observation using a clinometer. That's a small device that you sight through which measures slopes of fields. You can utilize average land slopes from soils maps. Remember, each soil name on a soil map will usually have a final letter which represents the slope range of that soil. You can combine those into weighted areas and get a weighted average. You can also measure slopes from topographic maps, just kind of combined areas with similar slopes and also create a weighted average of that. And also a contour length method is used pretty frequently, in that you just measure up the length of the physical contours and put them into the formula divided by the area, and that'll give you an average slope. But since this is a GIS focused course, we're going to be using the GIS method of computing a watershed slope. And that's going to be starting with a smooth, kind of low resolution DEM raster. We have 10-meter DEMs for the entire state, and those are perfectly suitable for computing these watershed slopes. And from those elevation rasters, we're going to create a slope raster and then compute the average slope inside a watershed polygon. Now, flow length is fairly straightforward to calculate. It's just the longest flow path in your watershed from the furthest point to your design point. It's measured in feet, and it usually includes the main watercourse and a tributary in the watershed. So if you have a ditch at your design point, the longest flow path is probably going to come down through the watershed into your ditch. And remember, water flows perpendicular to the contours. You won't have water going also, you won't have water going parallel to a main watercourse for any length. And I'll show what that means in a minute. Here's the two examples from the EFH2 manual. Just has a natural watershed on one side and a watershed with terraces on the other. Remember, you could have a rural watershed with man-made agricultural features that alter the landscape. It's still a rural watershed. You can still use EFH2 methods, but you'll have some man-made diversions that alter the longest flow path down through. So here's one with some Lidar contours shown. If you're looking at these three flow path options, which one would you pick? It's kind of hard to see, but there is a channel underneath this middle orange one, and that's important to know. If you have channels in your watershed, likely the longest flow path is going to come down through them. So you could look at this short orange one, and trash that pretty quickly. That's not the longest. This other middle orange one is definitely longer. Now this red flow path, I'm not sure it's really perpendicular to contours here, but maybe if you put it further out, it would be perpendicular, and you could imagine it coming all the way down here. And that would be longer than this middle orange one, but it's not a likely flow path. It's more likely that water from this area will make it to the main channel instead of going parallel to it. Alright, so we have a video for ArcMap users going over the details of how to download your DEM rasters and process them to compute the average watershed slope. We're going to be using the lag method to determine the time of concentration for our rural watersheds. The lag method requires two important inputs. First is the longest flow path. Now, the longest flow path can be estimated pretty much by taking the furthest point in the watershed, coming down perpendicular to the contours, and following that path all the way to the design point. The second component we need is the average watershed slope. And that's a little bit more tricky to compute. NRCS has developed several hand methods that the soil and water districts have been using for decades to determine the average watershed slope. But GIS professionals have their own method, and that's what we're going to be learning today. We're going to be learning how to use our GIS software to determine average watershed slopes. And to do that, we're going to need to download DEMs. I covered this a little bit in the Lidar lectures, but I'm just going to quickly review it here as well. For those of you in New York, which is what this course is geared towards, you're going to go to the New York State GIS Clearinghouse, find the ortho imagery link, and then open the digital ortho imagery application. It's a little bit confusing. This is also the place where you download aerial photos. They just bundled the download DEM function into this here. So you'll zoom into an area of interest. You have to be zoomed in quite a ways to be able to download. Say for this area, go over and look for the download button. It's a file folder with an arrow on it. Click that. Download in the current view. And then a panel will pop up on the left, giving you the available ortho photos and the available DEM results. So for this area, the only DEMs we have available are USGS DEC 10 meter DEMs from Cougar. We have 10 meter DEMs for the entire state of New York. In other areas, there'll also be a 2 meter, 4 meter, 5 meter, what have you, Lidar results. So wherever your area is, I encourage you to download the highest resolution data. If there's Lidar available, use that for your watershed, time of concentration, and delineation. If only 10 meter DEMs are available, use that. That'll work too. Here we have a DEM that I've downloaded in QGIS. It's a 2 meter LiDAR dataset in the town of Argyle, and I also have a watershed drawn in and contours displayed. Now remember, each pixel in a DEM represents an elevation. The brightest whites are the highest points and the darkest blacks are the lowest points. Now, since we have the elevation at each point, we can determine the slope at each point by comparing the elevations to its neighbors. And fortunately, GIS has a processing algorithm built in to do that function. So what we're going to be doing is creating a separate slope raster where each pixel has a slope value instead of an elevation value. Now to find that tool, you're going to look for the processing toolbox. If that's not open, you can look for processing up here and click the toolbox option. And in here, we're just going to search for a slope. Okay, and it actually has multiple slope options because QGIS is kind of a combination of multiple GIS packages. So there's a GDAL slope tool, there's a GRASS slope tool, and there's a Saga slope tool. So we're just going to be using the GDAL version, but you can feel free to check out the other versions. They're all fairly similar. So in the slope input box, we're going to be selecting the input layer. That's just going to be the DEM with all the elevations. Okay, the band number is 1. These options, the only one you want to click is the third one, slope expressed as a percent instead of degrees. For more advanced hydrology modeling, there's algorithms that use degrees of slope, but for the EFH2 method, it's expecting a percent rise instead. So click that. Okay, the scale is not really to convert between English and metric. The scale is to compensate in case your vertical units are different from your horizontal units. So in the old days, some DEMs were in decimeters, so you would have to convert your ratio between decimeters and meters. In this case, the DEM values are in meters and the map units are in meters, so we can leave this as 1. We're going to give it a file to save it as. Okay, we're just going to call it the 2 meter slope _1. Okay, and then open an output after running it. And let me turn off the 2 meter one. And turn off the contours. Alright, now we have a slope raster where each point represents a slope instead of an elevation. Again, the brightest whites are the steepest slopes. As you can see in the key, it goes all the way up to 45%. And then the darkest colors are the shallowest slopes. Now, in order to compute the average slope in our watershed, we're going to be using a zonal statistics tool. Okay, and that's built into the raster menu in just the native QGIS. So you look for the raster menu up top, look for zonal statistics, click zonal statistics. Okay, the raster layer that we're working on is going to be slope. That's what it's called over here in the legend. The polygon layer containing the zones. Okay, in this case we only have one zone. It's just in our watershed shapefile. okay, and it's called TC testing. Now the output column prefix, this is because it's going to put our zonal data into the TC testing attribute table. And if we want to do multiple runs, we're going to have to designate them with a prefix. So in this case, I'm just going to call it Tim underscore. Click OK, and that'll run. Okay, now you need to go to the TC testing attribute table, and it'll have your zones in there. In this case, I've already done one run, but I didn't delete it. So this is the one we're looking for. It's Tim underscore, and gives you the count, the sum, and the mean for that zone. So for this instance, what we're looking for is the average watershed slope, which is signified by the mean. And here it is, 17.06%. So once you have your longest flow path through the watershed and your watershed average slope, you can take these two valuable datas to EFH2, input them in, and it will compute the time of concentration via the lag method. I just want to quickly mention that there is ongoing research into whether using the highest resolution Lidar data, whether that produces the most accurate results for a watershed model. There's definitely research into whether coarsening the model to a lower resolution will give more accurate ground slopes. But that's definitely beyond the scope of this course. I just want you to know that there is some debate in the industry about what is the most appropriate use of Lidar for watershed modeling. And feel free to check out that research. It's all over the web. You can find it on your own. For your watershed projects, feel free to use the highest resolution Lidar files off the clearinghouse and just use them natively without coarsening or smoothing them at all. Up until now, everything we've covered pretty much applies uniformly to rural hydrology and urban hydrology. However, the time of concentration calculation is usually a bit different for urban hydrology, but that depends on the jurisdiction you're working in. Since this course is primarily intended for New York State designers, they would be using the New York State Stormwater Design Manual. Okay, if you're in another state, this might not apply to you, or if you're overseas, it definitely doesn't. So what's the caveat in the Stormwater Manual? It says TR55 and TR20 or approved equivalent shall be used for determining the peak discharge rates. Remember this, if you use the Stormwater Manual, you know that there's kind of separate requirements for water quality control from water quantity control. But your hydrologic model is primarily going to be used for water quantity control. You're determining the peak flow for the 24-hour storm events. The other thing in the Stormwater Manual is this down here. It says the length of overland flow used in time of concentration calculations is limited to no more than 100 feet for post-development conditions. And this is important because in the TR55 manual, it says you can use a limit of up to 300 feet. And that's important because this sheet flow or overland flow is a major component of the time of concentration. Flow overland in this fashion is very slow, so a longer distance makes your time of concentration much, much longer, which reduces the peak flow in your hydrograph. So this 100 feet is fairly limiting. In the TR55 manual, they specify 300, but that's really only for ideal flat surfaces like perfectly paved parking lots, and just doesn't happen in nature or in regular built construction. So you might remember from a previous lecture I mentioned TR55, Urban Hydrology for Small Watersheds. It's basically the manual for the TR20 computer program. Okay, the TR20 doesn't really have a user guide or a manual. You're just supposed to read TR55 and pick out the relevant details. But TR55 in itself is a hand method for doing the TR20 method using worksheets. So we're actually going to look at one of the worksheets in it. The time concentration worksheet is split into 3 segments. The first is sheet flow, or overland flow, as it's called in the New York State Stormwater Design Manual. This is the first flow path of the water. When the rain lands on the surface, it flows along the ground in a very thin sheet. After 100 feet, it switches to shallow concentrated flow. And this is even less defined than the sheet flow. It's kind of channeled into little ripples. It's like between sheet flow and channel flow, but neither of them quite. And then once you find a channel in your watershed, you need to model that as channel flow. So it's fairly subjective separating out these three segments in a watershed. Typically we just say sheet flow is 100 feet, and then we find the first recognizable channel in the longest flow path, and then whatever distance between that 100-foot mark and the first channel, we just call that shallow concentrated flow. So it's a fairly subjective experience, and that's why in some jurisdictions they don't use this TR55 method. They just use the curve number or lag method, which we learned for rural watersheds. But in New York State, you should be using this TR55 segmented method. Let's quick look at some of the inputs that go into each one. For sheet flow, you've got surface description, the Manning's roughness coefficient, flow length, the 2-year 24-hour rainfall. We'll cover where to get rainfall amounts when we look at the software in the next section, and the land slope. And that just goes into a formula and it computes it. Shallow concentrated flow is even less inputs. You just need the flow length, the slope, and average velocity, and the surface description. And these are all in a calculator in HydroCAD, which we're going to look at in a minute. For channel flow, it's the typical channel parameters, and these are for the bank full flow typically. So you'll need to have survey data or be able to come up with a good estimate for your channel size. Here's the example from the TR55 manual. It's just a watershed, supposedly in Tennessee, and they give you the design data for each one of these segments. 100 foot of sheet flow, 1400 foot of shallow concentrated flow, and then 7,300 feet of channel flow. So they have this all worked out in the TR55 manual, so I'm not going to go through that with you right now, but I would like to put all the inputs into HydroCAD to show you where to put them, and then we can check our answers against the manual and see if it comes out the same. So let me jump over to HydroCAD. In HydroCAD, once you've got a project started and a subcatchment added to the watershed, or added to the project, you just double click on it, and here's where you enter all your parameters for the watershed. The area tab is where you compute your weighted CN value, and the TC tab is where you compute the time of concentration. So we'll just look at the design data from the TR55 example and start adding it in. The first is going to be sheet flow, so you click the Edit TC button. Here's where you select which method. They do offer the lag CN method for rural watersheds. That's what we learned for the rural lectures. But I'm going to do sheet flow here. Description, I'm just going to call it sheet. Surface description, they're saying it is dense grass. So that populates the Manning's number. The flow length is 100. The 24-hour 2-year rainfall is 3.6 inches. That's already typed in there. And then the land slope, dense grass slope is 0.01. And that's in feet per feet, not percent. Okay, once that's in, just click OK. The next one is shallow concentrated flow. Surface description, unpaved. The flow length is 1400. And the slope is also 1%. Click OK. And finally, the channel flow. The area is, let's see, 27 square feet. The wetted perimeter is 28.2. The slope is 0.5%. And Manning's N is 0.05. Flow length, 7,300 feet. All right, so that adds up the time of concentration for each one of these segments and adds them together, and you get 91.9 minutes. So let's jump back and look at what the TR55 total time was and see if they're the same. And here's the result from the TR55 worksheet. It's 1.53 hours. So you can do the math. 91.9 minutes is 1.53 hours, so they match. Now, I encourage you to look at that through that example and the filled out worksheet 3 in the TR55 manual. Hopefully you've reviewed that manual already, but if you haven't, go ahead and take an opportunity to do that. All right, in the next section we're going to be looking at the software packages themselves, EFH2 and HydroCAD, and how to use them. We'll also be covering where to get the rainfall data to input into those. EFH2 is the program we're going to be using for our rural hydrological models. Now this data in particular only applies to practices that are built in New York State. We have New York State rainfall and New York State distributions. Well, actually they're for the northeast of the United States. But if you're using this program in another part of the country, you'll have different rainfall and different distributions possibly. So you just go to the NRCS Engineering New York website, scroll down to the bottom, and they have a whole section on EFH2. If you click down here, you can read these paragraphs. There's even a supplement that you can read. Contains all kinds of good data. But for now, just click over to the Storm Distribution Regions map. That's this colorful one over here. And each county area has either one or two storm distributions associated with it. Okay, it's type A, B, C, or D. Some counties fall entirely within one type range, and others have these border areas which you can click, and it'll give you a little inset map to show exactly where they want you to stop using type A and start using type B. So before you even open up EFH2, you'll need to go to this map and figure out what rainfall distribution you're going to be using. In addition, as far as rainfall amounts, they come preloaded with EFH2 for New York and many other states, but not all of the states. In New York, we have some counties that have two rainfall amounts. Okay, most have only one rainfall amount. You'll just pick that from a drop-down in EFH2, but some have split amounts. So say for this county, you have Steuben North and Steuben South. Okay, so you'll need to know whether you're north or south, because it'll be a different rainfall amount that you'll select in EFH2. As far as downloading and installing EFH2, it's fairly straightforward. You can search for EFH2 NRCS download and just get it. You just download it here. Now once it's installed, you do need to change the name of one of the data files, and I'll show you how to do that now. You'll just go to Computer, your C drive. You're looking for program files, which might be program files x86 if you're in 64-bit Windows. Scroll down and look for a USDA, and inside there, EFH2. You'll see a whole bunch of rainfall files. They're just called county dot and then your state abbreviation. All right, state county.ny is included, so that's good for our purposes. But keep going down and you'll find a bunch of type files. Okay, there's different distribution type files for different parts of the country, and there's one for the original type 1, type 2, type 3. Now I've already done this. I've taken the original type file and renamed it as type original, and then I've taken the type _ northeast file and renamed it to be type.rf. Okay, you don't need to keep the original type file. It just has 1, 2, 3, 2a in it, but you need to rename the type _ northeast file to be type.rf in order for the program to find it. It's looking for that type.rf file, and it won't even see these other ones. All right, but if you're in a different part of the country, one of these other ones might be appropriate. I'm not actually sure, so check with your state engineer for NRCS. Now once you have that figured out, you can run the program. It's in Engineering Applications, EFH2, EFH2. The first tab is just an introduction. It has kind of the same caveats that the website shows, just kind of the limitations that it's intended for, 1 to 2,000 acres, watershed slope limitations, and hydraulic limitations. So let's jump to the basic data page and see what needs to be input there. Client doesn't need to be filled in, you can put whatever you want. State is where you put in your 2-letter state abbreviation. Until you put that in, this county dropdown won't work right. Alright, it'll say please enter the state abbreviation. So I'm going to put in New York here, and that'll tell it to use the county.ny rainfall file. And as I scroll down the list, well, let's just look at Albany. Albany has a north and a south. But you see here in this list, it has 2 souths listed. That's just a reminder to the user that there are 2 distribution types for that area. So Albany South has a specific rainfall, which is different from Albany North, and there are also B and C distribution areas in that Albany South area. And now selecting this B or C doesn't actually select that distribution in the program, it's just a reminder that you'll have to do that later. So say we're in Albany South, Northeast Regional Climate Center C, you can select it here, that'll select the rainfall amount, but to select the distribution you have to go to the rainfall discharge data page and select it manually there. So it's going to be NRCC C. Go back to basic data. We need to type in drainage area, say it's 100 acres. Runoff curve number, you can type this in directly or you can use the calculator that's built in. Let's check that out quick. Has all the A, B, C, and D soils for each soil cover type that's covered in the Tier 55 manual or in the FH2 manual. You have the urban areas, residential districts, all that kind of stuff. Let's go down to agricultural lands and say we've got 50 acres of bare soil in B and row crops in D soil, 50 acres too. Alright, so that'll compute a weighted curve number of 86. You can accept it here and it'll populate that box back on the basic data page. Watershed length, that needs to be a number more than 200, I believe. Yep, 200 to 26,000, so let's say 500. Watershed slope, 12%. And that gives it a warning. Now the calculated time of concentration is 0.06 hours. TC is adjusted to 0.10 hours. That's okay. If your time of concentration is below that minimum, it'll just bump it up to the minimum of 0.10 hours. That's fine for your model. Nothing to be too worried about. Once the basic data is input, it just calculates it in the background. So when you go to the rainfall discharge data tab, your peak flows and runoff inches will already be calculated. It's just looking up these 24-inch rainfall values from that county.ny data file, inputting those, running the program, and getting your peak flow in CFS. Now you'll notice if you look around, there's no place to find a hydrograph. It's not doing that for you. So if you need to route a hydrograph through a practice, this program is not for you. It's only going to compute the peak flows for your practices like diversions or ditches or what have you. Anywhere where you just need a peak flow and not a total hydrograph. Alright, the next lecture is going to look at kind of doing the same basic inputs into HydroCAD for doing more urban sites or larger rural areas. HydroCAD is the hydrological modeling software we should be using for urban watersheds and any rural watersheds that exceed the limitations of EFH2, plus any watershed projects where we want to develop a full hydrograph, say for pond routing or storage. One of the kind of quirks of HydroCAD is that there's a variety of rainfall and storm distribution types currently allowed in New York State. Okay? Remember, we should be following the New York State Stormwater Design Manual. That allows you to use the Tier 55 storm distributions and rainfall, which are both somewhat out of date. So considering that this course is introductory and it's geared towards people just learning about hydrology, I'm going to suggest that you totally dispense with the type 1, 2, 3 distributions and the old TP40 rainfall data and just use the newer Northeast Regional Climate Center rainfall and storm distributions. Okay, we've covered this a little bit if you've watched the EFH2 lecture, and the rainfall and the distributions will be the same for this. If you are looking for information on it, you'll want to go to the New York NRCS Engineering website, pull that up and scroll to the bottom and look for the EFH2 section. That'll show the maps that you'll need when pulling this data into HydroCAD. First thing you need to note is the storm distributions regions. If you click on that, that'll bring up a map. You can see most of the counties in New York are fully within one distribution area, but some have one or two different ones. You'll just want to figure out where your project is located, and if it's in one of these border areas, click on the blow up and it'll show exactly where they want you to use the type A, type B, and so on distribution regions. One further thing you'll need to note from this website is the rainfall sub-areas. Most of the counties in New York have just one rainfall amount for the whole county, but some are split into two areas. So if your project is in one of these counties, you'll need to click on the map to bring up the inset, and then it's split up by towns. You can just figure out which towns are in Washington North and which ones are in Washington South. So from this NRCS engineering website, you're going to need to figure out which distribution to use, A, B, C, or D, and if your county has sub-rainfall areas, which one it's going to be in. Now let's jump over to HydroCAD and see where we get this data and which tables to pull it from. Just a quick note about HydroCAD, it's definitely the modeling package that I recommend for urban projects. And to test it out and learn it, you should use the HydroCAD sampler. The sampler is a free download. It just has a few limitations, being you can only use it for 60 minutes before it closes, and you have to reopen it, and you can only save project up to 5 nodes. Alright, in this project we're just going to be using one node, a simple watershed. So you download it and install that. I think you have to register too. I can't quite remember. I did it a while ago. When you start it up, it'll ask you to click OK to begin your 60-minute evaluation period. Then I'll do that. And once you get running, it'll ask you to click here to open or create a project. Alright, so I'm just going to create a new project called Tim. Create it. Now when I start a new project, the first thing I want to do is set up the calculation parameters, including the rainfall and storm distribution. To do that, look for the calculator button up at the top, calculation settings. Okay, on the general tab, just do runoff method SCSTR20. That's the method we're doing. For the reach routing and pond routing, just leave those as the defaults. You'll want to read up on what to use if you end up doing reach routing or pond routing. For this case, we're just doing a simple watershed runoff. Click over to the rainfall tab, and there's a few options here we need to select. On the storm type, remember how I said we're going to be using the Northeast Regional Climate Center distributions for this course? Click the drop down for that and scroll up until you find NRCC. Okay, expand that and do 24-hour. That's going to populate this drop down for A, B, C, or D. Alright, so depending on where your project is located on that NRCS New York engineering map, you're going to be picking A, B, C, or D for your storm distribution. Storm duration is going to be 24 hours. Back-to-back storms, this is an option you can play with if you choose. Definitely read the help file for what it means. Depth, this will be populated once we get rainfall events in. And AMC is the antecedent moisture condition. Just leave that at the default value of 2. Again, you can read the help file for what exactly that means. On all these dialog boxes, the help file is really useful. You can just click help. It'll come up and give links to all the terms that appear on that dialog. For rainfall, we're going to be doing an import events from the Atlas 14 database. Now the Atlas 14 database is pretty old, but it has been recently updated, and the latest version of HydroCAD has the most recent updates. These will have the same rainfall amounts for each county and sub-county area that NRCS is using for the EFH2 method and their rainfall files. So do import events from, and you want a lookup table. All right, HydroCAD comes with two lookup tables. There's TP40 and Atlas 14. So you want Atlas 14, and then scroll down until you find New York State. And once you get to New York, you'll have all those county rainfalls, and any counties that have subareas, you'll have those rainfall values as well. So say your project was in Schoharie County North. You can select that one. Select the storm distribution and click OK. And that'll bring all those rainfall events into your project. Okay, when you're running HydroCAD, you're going to select what year the storm is, so what year frequency. So for each run of HydroCAD, you're going to be selecting a 1 year, 2 year, 5 year, 10 year, 25, 50, or 100. Okay, and you can look at each of those depths here if you want to select them, whatever you want to do. Click Apply. Okay, and once you click Apply, those will show up in the main menu drop-down. All right, that's all you need to fill in on the rainfall page. Time span is next. Start time and end time, you can fiddle with those. For the TR20 method, which we are using, there's typically no runoff for the first few hours of a storm because the runoff has to exceed the initial abstraction. Okay, if you don't know what that is, you can look it up in the HydroCAD help. It's just the way the formula is set up. It's designed to model initial soaking in of rain so that runoff does not immediately run off to your design point. So just for consistency, let's do 0 and 24 for our 24-hour storm, just so we can see that there's no rainfall coming in those first few hours. Time increment is kind of like the step for the hydrograph. It just determines the number of hydrograph points. If you have something really complicated going on in your watershed, you could decrease this to get kind of better accuracy. But for us, let's just leave it at 0.05. Reports, unit hydro, advanced, resize. These are all kind of advanced ones that we're not going to deal with right now. But on each window, just click the help file and it'll tell you what everything exactly means. So let's click Apply, then OK to go back to the main window. To add a watershed, you just click and drag a subcatchment from this toolbar over on the left, and then right click and do Edit, and that brings up the 4 main tabs of the Edit window. General, you're just putting in the name, say the North field. Area, this is the CN calculator that you're going to put in your CN values that you came up with in GIS. For this, we'll just do a lookup. It gives all the lookup values that are in EFH2 and TR55. So look down to, say, straight row crops or bare soil. Let's say bare soil, type D. Okay, double click that, and we'll do straight row crops, B soil, poor. Okay, and just type in the acreage that you have for each of those, which you have mapped out of your drainage area. For time of concentration, remember we covered this a little bit in the time of concentration lecture. You can use either the lag method or the chopped up method, sheet flow, shallow concentrated channel flow. So if you're using the lag method, you just add it like this and type in your parameters, the average land slope, contour interval, contour length, hydraulic length. Okay, and it'll compute your time of concentration that way. Or you can put in each individual row. So if you put in sheet flow, it'll give you the ask for the parameters for that. And same with shallow concentrated and channel flow. So for the sake of this example, I'm just going to do direct entry. Type in 15 minutes and do OK. So that'll do a 15-minute time of concentration for this watershed. So once you have areas put in and time of concentration input and also rainfall added, then you can run the model and get a hydrograph. I'm going to click apply and OK on this window. And then you just want to drop down and pick the design storm. Say you want to do the 10-year design storm, then you double click on the node. Okay, check for any errors. It says hint, longer time span advised for full volumes. Okay, that means that this hydrograph has not quite come down all the way back to 0 at 24 hours. So if you need the whole volume of the storm, you'll need to extend that out. Here's the hydrograph. You can see the rainfall doesn't start producing runoff until about hour 7 of the storm. It comes up to a peak and goes back down. Alright, there's all kinds of options on this graph. Alright, you can do summary, hydrograph. It'll show the events. Okay, all these options are there too. Feel free to explore this program at your leisure. We're just covering kind of the basics of setting up a drainage area and computing the runoff. Alright, also YouTube has a ton of videos on HydroCAD, many produced by the software developer himself. So feel free to check those out if you want to get into more advanced modeling. We're just scratching the surface of it with this course. The rational method is a good hydrology option for modeling urban storm sewer networks, where the watersheds are fairly small. You don't need a pond routing analysis at the end, and things are fairly uniform. Now, if you're asked to do the rational method for your job, hopefully you work at a company that has either a Bentley or Autodesk subscription 3D package. I feel those packages are much better suited to doing storm sewer design because they formulate into 3D designs at the end of the day, and that helps you, design inlet elevations and pipe invert elevations. However, HydroCAD does have this functionality for modeling the rational method built in. So for this case, I don't have Bentley Inroads or Autodesk Storm and Sanitary, so I'm just going to be showing it in HydroCAD. But to use the rational method in HydroCAD, first you need to download an IDF curve. That is an intensity, duration, frequency curve. And in New York State, we get those from the Northeast Regional Climate Center. For most other states in the country, you'll get it from the precipitation frequency server that NOAA puts on. And a quick note, the Northeast Regional Climate Center server is going to get rolled into the precipitation frequency server sometime in the near future, but not sure when. So if you go to the Northeast Regional Climate Center site, look for Data and Products. It's like a tab that shows up at the top here. And click Extreme Precipitation Tables, text/CSV. Then locate your site on the map. Let's say here in Dolgeville, and double click. Then there should be an option at the bottom. You might have to scroll down to see it. For smoothing, you want no smoothing, and then click submit. Then however your browser set up, it might ask you to save the file, or it might just download it to your downloads file. Here I've just downloaded it. I'm going to open it. It's just a text file with a whole ton of numbers in it in a standardized format. However, we need to save it as an extension that HydroCAD will recognize. So go to File, Save As, and then you're looking for your HydroCAD program folder, which should be in C, Program Files, or Program Files x86, then HydroCAD, and then you want to put it in the IDF folder. Okay, so give it a name, call it New York, Dolgeville, and then the extension needs to be HCI, not TXT. And save it. Now when you open up HydroCAD, it will look in that folder and it'll be able to find that IDF curve. So I'm going to close this. Start up HydroCAD. And when I start up HydroCAD, I want to set up the rainfall data first. Well, first I'm going to open a project. I'm going to create a new one called New Rational. Create it. Then click the calculator button to set up the rainfall data. For the general tab, I'm going to click the rational method instead of the SCS TR20 method. Then on the rainfall tab, I need to point to that IDF file that I just saved. So you look for the IDF file drop-down, click it, and hopefully that IDF file is in that list. Here it's New York Dolgeville. Click that, and then for the event drop-down, you're going to need to put in whatever storm frequency you're designing to. And this will depend on the type of road or the road classification that you're creating your storm sewer network on. So for this case, let's do the 5-year storm. Okay, and it also asks for the storm duration. Okay, the duration for the rational method is equal to the time of concentration. And for most storm sewer networks, the minimum time of concentration is 5 minutes, and most real time of concentrations will be less than that. So for convention, we usually do 5 minutes. Then click Apply and OK. Now it's the same as a TR55 method for modeling. You just click and drag a subcatchment into the project area. You can right-click and edit it. Give it whatever name you want. Then on the Area tab, you put in your areas and C values. Now the C values sound like CN values from the TR55 method, but they're not the same. They range from 0 to 1 instead of from 30 to 100. Okay, so you have to just keep that in mind, that you're not using CN values in this column. So for this one, I'm going to input an area 1 acre, a C value of 0.98. Description, I'm going to call it a parking lot. Now there's no lookup table in HydroCAD for these C values. You have to get them from a hydrological reference. If you're in New York State, I highly recommend the New York State DOT Highway Design Manual, Chapter 8 on highway drainage. They have a nice chart in here which covers most of the scenarios you'd want. These C values are somewhat subjective. There's a good range on them here. And if you look at other hydrological references, they might have different values listed for each type of surface cover. So feel free to browse them and use them as you wish. But back to HydroCAD. Once we've got the C value listed and the area in, go to the time of concentration tab. And for most storm sewer networks, I said the time of concentration will be less than 5 minutes, but we use 5 minutes as a minimum. So I'm just going to put a direct entry in here of 5 minutes. Alternatively, you can calculate the time of concentration using the little lag flow method, sheet flow, any of these other ones, just like we would with the TR55 method. I cancel that. So once you have time of concentration and area, you can apply and go back to the project. Double-clicking the watershed produces a hydrograph with a peak flow. However, this is not a real hydrograph like you would use for pond routing with the TR55 or SCS TR20 method. So you're just going to be grabbing the peak flow from this diagram. Okay, kind of ignore the hydrograph. It's not a real hydrograph. Just use the peak flow for doing your design. I've created an urban hydrology scenario using the parking lot adjacent to my office building here in Albany. If you type 10B Airline Drive, Albany, New York, into Google Maps or your GIS platform, you'll come to this property, and our building is kind of in the back, set back from the road. So we're imagining that the landlords of this building here have decided to disconnect 2 of their catch basins and treat the stormwater with a hydrodynamic separator. So they need to know how much water is coming into each of these catch basins and what the peak flow will be for the 2-year design storm. That's their targeted design for treatment. So you're going to need to download the DEMs from the New York State GIS Clearinghouse. There's a 2-meter DEM available for this area. Download that and use that as your survey. Bring that into QGIS, display the watersheds, and then take those areas into HydroCAD and compute the peak flows. I have written instructions for both the rational method and the TR55 method, so you can follow those along to help you on your way. If you get stuck, shoot me an email or post a question in the course comments.